Hello everybody and welcome back to another visual pattern challenge. Here is our pattern today. It's a colorful one. We've got figure 1, figure 2, figure 3, figure 4, and your challenge is to predict the number of these hexagons in figure number 5. If you can do that, can you predict the number of hexagons in figure 43? And can you write an equation that could be used to predict the number of hexagons in any figure at all? So that is the challenge. If you'd like to accept it, pause the video and work it out. Okay, well, there seems to be a lot going on here. Sometimes when these patterns are color-coded, it can actually be confusing or counterproductive or not help us visualize the pattern. In this case, I think it's actually very, very helpful. So let's try to predict the number of hexagons in figure 5 by just looking at each color on its own. So first, in the blue, I have 1, and then I have a 2 by 2 square, and then I have a 3 by 3 square, and then a 4 by 4 square of blue hexagons. So for the blue, I think I'm going to have a 5 by 5 square. And then let's see, with the reds, I've got 2, and then 4, and then 6, and then 8. So I think I'd have 10 hexagons in the red. And then looks like every step has this green one. So add one more. So 5 times 5 is 25 plus 10, 35 plus 1 is 36. So I'm going to predict 36 hexagons in figure number 5. Now let's take a moment to analyze the numbers here. I think I know what kind of a pattern this is going to be. The squares are giving me a big clue that this is quadratic. But let's go ahead and just look at the numbers and see if that's validated. In step 1, we have 4 hexes. In step 2, that's 8, 9. In step 3, that's 16. And in step 4, or figure 4, let's see, that's 25. And for figure 5, we're predicting 36. Now, you may already see something that jumps out at you from these numbers, but I want to look at creating an equation based on the colors. But first, let's go ahead and take our differences. So 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 16 is 9, 36 minus 25 is 11. You're seeing we're not getting a constant in our first set of differences. So it's not a linear pattern. I didn't think it was. I was thinking quadratic. So let's take the second set of differences. 7 minus 5 is 2. 9 minus 7 is 2. 11 minus 9 is 2. Yes. So this constant in the second order differences means the pattern is quadratic. So it's got an x squared in it somewhere. So let's look at these colors. I've got here the blue is first 1, and then it's 2 by 2 square, 3 by 3 square, 4 by 4 square. That is the step number squared. So I think the blue is x squared. Now, what is the red? First it's 2, then it's 4, then it's 6, then it's 8. That seems to be taking the figure number and multiplying it by 2. 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. So I can write that as 2x, 2 times x. And then we just have this green one, and it's always just the same every step. It's just that extra 1. So this could be an equation for our pattern. And if you want to test that, let's try it with figure number 3. That would be 3 squared plus 2 times 3 plus 1. That's 9 plus 6. That's 15 plus 1 is 16. So that matches the number of hexagons in step 3. And you could try this, test it out with each one. I don't think we need to, because really we created this equation directly from the numbers that were here. So probably this makes sense in your head already. Now there's another way to arrive at an equation for this one. You may have seen that these numbers 4, 9, 16, 25, 36, maybe that jumped out at you as all being perfect squares. 4 is 2 squared, 9 is 3 squared, 16 is 4 squared. And really what these numbers are is the step number plus 1 squared. So you might have come up with this equation, y equals x plus 1 quantity squared. So in step 1, it would be 1 plus 1, 2 squared, that equals 4. In step 2, 2 plus 1 is 3 squared, 9. That works too, and you can test it with all these other steps. How come we have two different equations? Well, If you FOIL out x plus 1 squared, so the x plus 1 times x plus 1, x times x is x squared, x times 1 is x, 1 times x is x, and 1 times 1 is 1, and then you combine these like terms, you get x squared plus 2x plus 1. So this is really the same equation. And either way you write it is just fine. I'm going to write it like this because it matches the colors we have, x squared plus 2x plus 1. Now, all we have to do to calculate the number of hexagons in figure 43 is to plug 43 in for x. Don't forget to plug it into both places. So y equals 43 squared plus 2 times 43 plus 1. Now, 43 squared is 1,849, and 2 times 43 would be 86, and then plus 1. So that would be 16. That'd be 13. So I'm getting 1,936. Is that what you got? Did you get 36 for figure 5? Let me know. Thanks, everybody.